This lesson is on molecule polarity. So we've talked about bond polarity, but now we want to know, is the molecule as a whole polar or nonpolar? So we're going to need to be able to draw the Lewis structure, determine the geometry of the molecule, and evaluate the polarity of the bonds in the molecule. So for this lesson, you will need the periodic table of electronegativities. So either a printout or you can refer to the charts on pages 161 and 176. You will also need your notes on electron set geometries and molecule geometries. So first we're going to start out with a definition of a dipole moment. So we talked about a dipole, which means we have a positive end and a negative end, a separation of equal and opposite charges. The dipole moment is the sum of dipoles in 3D space. So this is the sum of dipoles in 3D space. So this is a special kind of addition. I don't know if you've heard this word. This is vector addition. So you'll first encounter that probably in your mathematics class. It's heavily used in physics. We're not actually going to do the vector addition. We're just going to qualitatively evaluate if we have a dipole moment or not. Okay, so how does that relate to molecule geometry? Molecule polarity. Okay, so our molecule can be polar or nonpolar. All right, when we have a polar molecule, our dipole moment, our sum, does not equal 0. So for a polar molecule, the dipole moment does not equal 0. So our dipoles do not cancel each other out, and the entire molecule has a net dipole. That means the sum. So we have a positive end and a negative end. In our molecule. So we'll just represent a molecule here. So one end would be positive and the other end would be negative, and that would be like delta plus delta minus. Now, our polar molecules are affected by an electric field. And we'll talk about what that means, but whenever you see electric in chemistry or physics, we're talking about charges. All right, so our nonpolar molecule, our dipole moment does equal 0. And that is because our dipoles cancel out. So we do not have a positive end and a negative end of the molecule. And so our molecule is just there. Our charge is evenly distributed, and our nonpolar molecules are not affected. by an electric field. Okay, so let's do a little drawing to kind of illustrate what we mean by that. Okay, so we are going to have an electric field. So we're going to have a plate of metal and another plate of metal. So they're just thin little pieces of metal. And one side we're going to charge up to be positive. So this metal plate has a positive charge, and this metal plate has an equal and opposite negative charge. And to understand how that works, you'd have to do some physics. Okay, so we have empty space in the middle, a positive plate of metal, and a negative plate of metal. So now we take our non-polar molecules and put them in our space. And they just go through. They're not affected. They just go through and come out. And they go through, we'll use a chemistry term here, just kidding, willy-nilly. They're not affected, they just go through. They're not bothered by that electric field. So now, we take our electric field, our two metal plates, one's charged up to be positive, the other one charged up to be negative. And now we take our polar molecules. Now remember, polar molecules have a positive end and a negative end. And we put them through the empty space between the two plates. And now our molecules are going to orient themselves because the positive part of the molecule is going to be attracted to the negative plate. So the positive part of the molecule will be here, and the negative part will be over there. So all our molecules will have the same orientation in terms of the positive part and the negative part. So they turn themselves around in the field because of the different attractions that the ends of the molecules have for the plates. Okay. So now we're going to analyze some of our polarities of molecules. So we're going to start with our simplest molecules, our diatomic. Our diatomic molecules. And remember that our diatomic molecules, they have one bond, and the geometry is linear. They're in a straight line. The only way to connect two molecules is in a straight line. Nucleus to nucleus, straight line. They're linear. And since we only have one bond, whatever the polarity of that bond is, that is also the polarity of the molecule. So we can say that for diatomic molecules, the bond polarity is equal to the molecule polarity. So if we look at a molecule of bromine, one of the Hofprinkel elements, the molecule is two bromine atoms bonded together. So if we look at our Lewis structure, and we do our valence electron counts, bromine is a halogen, it has 7. So we have 7 and 7, we have 14, so we put those in. And there's our Lewis structure. And these bonding electrons are being shared equally. If we look at the bromine bond in terms of electronegativities, consulting the chart, bromine has a value of 2.8. So our delta, of course, is 0.0, meaning we have a non-polar covalent bond. So that means that the bromines are sharing these bonding electrons equally. Each bromine is pulling on them with the same amount of force, so it is equal sharing. So since we only have one bond, this means that a bromine molecule is a non-polar molecule. All right, so now if we have a molecule of HBr, so hydrogen is 1 valence electron, bromine has 7 for a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And we want to evaluate the bond. Of course, our geometry is linear. We have H and Br. So we check our periodic table of electronegativities. Bromine is 2.8 and hydrogen is 2.1. So our delta, our difference is 0.7. And we look on our chart. This means that we have a polar covalent bond. So with a polar covalent bond, our more electronegative element gets the delta minus. Our less electronegative element gets the delta plus, meaning these bonding electrons are not being shared equally. Bromine has the greater electronegativity, the greater pulling power. It pulls those electrons towards itself and ends up with a slight negative charge. So one bond, our bond is polar covalent. That means that our molecule is polar. So we have a polar molecule. So HBr would be affected by an electric field. Bromine, Br2, would not be affected by an electric field. So for diatonic molecules, it's pretty easy. Evaluate the bond, whatever that is, that's what your molecule is as well. Okay, what about when we have molecules with 2, 3, or 4 electron sets? Two, 3, 4, 4 electron sets. To determine the polarity, we're going to look at the geometry of the molecule as well as the bond polarities. So we're going to look at the geometry of the molecule and the bond polarity. And both of these together are going to help us determine the polarity of the molecule itself. Okay, so let's look at 2 examples here. We're going to look at carbon dioxide, and then we're going to look at a molecule of OCS. So I'm not going to write down the valence electrons. You can do that on your own. I just want to save time in this video. So with carbon dioxide, carbon has 4 valence electrons, each oxygen has 6. We have a total of 16. And when we put them in properly, for every element to have the octet, I'm going to end up with double bonds between the carbon and the oxygen. Okay, we have 2 electron sets. So our geometry is linear molecule geometry, as well as electron set geometry. All right, and now we're going to evaluate the bond polarity. So we have to look at the carbon-oxygen bond. So using our periodic table of electronegativities, we can see that carbon is 2.5 and oxygen is 3.5 for a delta of 1.0. This is in the range of polar covalent. So that is a polar covalent bond. So now we're going to look at our molecules. We have carbon, double bonded oxygen, double bonded oxygen, Just rewriting our Lewis structure. So our polar covalent bond, our element with the greater electronegativity, gets a delta minus. So there's a delta minus on that oxygen and a delta plus on that carbon. For this bond, we have a dipole that looks like that, going from the positive to the negative. We also have another bond. Our oxygen, being more electronegative, gets the delta minus. Our carbon gets the delta plus. So we have a dipole going that way. These two dipoles are exactly equal and opposite. So these dipoles cancel out. So our equal and opposite dipoles cancel out. So that means that we have a non-polar molecule. Okay, so that might be surprising because our bonds are polar, but our molecule is non-polar. The dipole moment equals 0. Equal and opposite cancel out. Okay, if we look at OCS, now we have the same number of valence electrons because oxygen and sulfur are in the same group of the periodic table. We get the exact same Lewis structure. So we have the exact same geometry. We have a linear molecule geometry. And we have our carbon-oxygen bond we've already evaluated. That is polar. And now we're going to look at our carbon-sulfur bond. So carbon, we already looked that up. That's 2.5. And according to our chart, sulfur is also 2.5. So our delta there is 0. So the carbon-sulfur is a non-polar covalent bond. So that means that the carbon and sulfur share these bonding electrons, these 4 electrons, they share them equally. So let's evaluate that. So we have oxygen double bonded to carbon, double bonded to sulfur. So for this bond here, we have a delta minus on the oxygen and a delta plus on the carbon. So we have a dipole going that way. And then we don't have a dipole here. We said that these electrons are being shared equally, so that's it. So this does not cancel out. Our molecule has a dipole with the negative end at the oxygen and the positive end at the sulfur. So this is a polar molecule. Looking at these two molecules, they have the same geometry, but because this one has 2 polar bonds that cancel out, it's nonpolar, but this one, the dipoles do not cancel out, so this is a polar molecule. This one would react to an electric field, and this one would not. Okay, let's look at another example of this, and we will look at B, Cl3, and B, Br, Cl2. So first we do our Lewis structure. We count up our valence electrons. We have 24. We put boron in the middle, chlorines around, and put in those 24 electrons. And remember that boron is often an exception to the octet rule, which it is in this case. Chlorine, halogen, only wants to make single bonds, so boron's going to have to make do with having 6 electrons around it. So we have 1, 2, 3 electron sets. So our molecule is trigonal planar. So we're going to draw it to represent its geometry. And now we're going to evaluate the boron-chlorine bond using our periodic table of electronegativities. Boron from the chart is 2.0. Chlorine from this chart is 3.0. with a difference of 1.0, which puts us in the polar covalent bond category. So that means that chlorine is more electronegative. It has a greater pull on the bonding electrons. So the chlorine gets the delta minus, whereas boron gets a delta plus. Each chlorine gets delta minus, and the boron gets delta plus. So now we have dipoles going like this, up, down, over. And these are three equal and opposite. So if you had three ropes connected and you had three people pulling on them exactly equally, the rope would not move. These dipoles do cancel out in 3D space. So we have a non-polar molecule. So again, we have an example where our bonds are polar, but the molecule itself is nonpolar because these dipoles cancel out. For BBrCl2, now bromine and chlorine have the same number of valence electrons. We're going to get the same Lewis structure. So we're going to have boron in the middle with a bromine and then our two chlorines. And we already did our bond evaluation for boron chlorine. So our chlorines have a delta minus, giving a delta plus at the boron. But now we have the boron-bromine bond to evaluate. Boron 2.0 and bromine is 2.8. So our delta is 0.8. And that still puts us in the polar covalent bond range. So we are not sharing electrons equally between the boron and the bromine. Bromine is more electronegative. Bromine has a delta minus. However, the bromine-boron bond has a lower difference than the boron-chlorine. Chlorine's stronger. Chlorine's pulling electrons towards itself better. Chlorine is producing more of a dipole with the boron than bromine is. So our bromine still has a delta minus, but it's a little bit smaller than the chlorines. So if we were to draw those dipoles, the one for the bromine is a little bit smaller. So these do not cancel out. Again, if you had three ropes and the two people here were pulling and the one pulling this way was pulling less, the rope would be moving down. The molecule has a dipole. The sum of these dipoles is a single dipole going down. So this is a polar molecule. Our bonds are polar and our molecule is polar. So just changing one atom, it doesn't change the geometry, but it does change our dipoles. Okay, so now let's look at CH4. And we're going to see the same thing here, so we'll go through this pretty quickly. And CH3Cl. With CH4, we've got 8 valence electrons. We have a tetrahedral geometry. So one hydrogen goes up, one goes off to the side, one sticks out the front, and one sticks out the back. Evaluate the bond. So carbon, what did we say carbon was? 2.5. Hydrogen is 2.1. Our delta is 0.4, meaning we have a, oops, I forgot to write polar covalent bond. But it's slightly polar. I mean, that's a really low value. It's polar, but slightly polar. So here, Our hydrogens get the delta plus, and carbon gets the delta minus. And then carbon gets all those delta minuses. Okay, so this is going to be tough to draw these dipoles in 3D space, but I will tell you that they cancel out. Vector addition, they cancel out. So we have a non-polar molecule. Non-polar. Our dipoles will cancel out. However, with our next molecule over here, so here we have chlorine, hydrogen. Changing one of those bonds to chlorine, let's look at the carbon-chlorine bond polarity. Chlorine is one of the third most electronegative elements on the periodic table with a value of 3.0. And then carbon has a value of 2.5. So we have a value of 0.5. So this is also polar covalent, but it's stronger than the carbon-hydrogen bond. And here the carbon has the delta minus. Here the carbon has the delta plus. That is the delta minus. So that means we're going to have a dipole going up towards the chlorine, and then these three dipoles are going to be heading into the carbon. So that means that our dipole moment is going to be up. We'll have a negative end of the molecule at the chlorine and the positive end of the molecule down at the hydrogens. So here we have a polar molecule. So when all the outside, the terminal atoms are the same, our molecule ends up being nonpolar. We make a change, just change one of our hydrogens to a chlorine, and that turns our molecule into being polar. Okay, so now we're going to take a look at water, a very, very, very important molecule. We would not be alive without it. So H2O, when we do the Lewis structure for that, add up our valence electrons, we get 8, 2 from the hydrogen, 6 from the one oxygen. And we have 1, 2, 3, 4 electron sets. Our electron set geometry is tetrahedral, but this means that our molecule geometry is bent. So we have oxygen. I'm just going to draw it this way. Just show those lone pairs right there. I'm just showing the bent shape of our water molecule. We evaluate the OH bond. Oxygen, second most electronegative element on the periodic table at 3.5. Hydrogen at 2.1 for a delta of 1.4. So this is polar covalent, and it is very polar. Has a large electronegativity difference. So the oxygen has the larger value. There is a delta minus at the oxygen, a delta plus at the hydrogen, delta minus here, delta plus there. So our dipoles going from the positive look like this. So they do not cancel each other out. They are both pulling up. So this is a polar molecule. And that influences a lot of the properties of water. We would not have life on Earth if water was not a polar molecule. So our dipoles do not cancel out. And let's look at one last molecule, NH3, which is ammonia. If we do our Lewis structure, again, we have 4 electron sets, giving us a tetrahedral electron set geometry. And because we have one lone pair, our molecule geometry is trigonal pyramidal. So drawing that kind of like we see it, we have a nitrogen And then we've got our hydrogens below it. One sticking out in the front, one going behind in the back with our lone pair of electrons. Look at the nitrogen-hydrogen bond. Nitrogen, here's my table. Nitrogen, oh, I should have known that. It's third most electronegative along with chlorine is 3.0. Hydrogen is 2.1 for a delta of 0.9, giving us a polar covalent bond. Nitrogen, being more electronegative, gets the delta minus. Delta minus here, delta plus at the hydrogen. Delta minus, delta plus, delta minus, delta plus. So our pluses are all below the nitrogen. So our dipoles are all pointing up towards that nitrogen. So they do not cancel out, they're pulling up. So we also have a polar molecule. Okay, so now I'm just going to sum up. So we can certainly go through that whole process to figure out the polarity of our molecules, but we kind of have a little shortcut here. So remember, if we have two atoms in the molecule, then whatever the bond is, that's what the molecule is. But if we have 2, 3, or 4 electron sets, then we have a non-polar molecule if all the terminal atoms are the same. They're the atoms on the outside. If all the terminal atoms are the same. So they can be all hydrogens or all chlorines. Doesn't matter as long as they're all the same. And this is real important. There are no lone pair electrons on the central atom. And no lone pair electrons on the central atom. So the atom in the middle can't have lone pairs, and the atoms on the outside, the terminal atoms, all have to be the same. So that means we have a polar molecule if it's the opposite of this. We have different terminal atoms. You only need one to be different. Or you have lone pair electrons on the central atom. So these two things mean exactly the same thing. So learn one of them, and then it's always the opposite for the other one. So that's it for today.